These slides begin the introduction of anti-causal sequence. In this particular case, we examine this, and we want you to remember that we have examined a very similar sequence that looks like this, where this is the causal sequence, and this has a Z-transform that looks like this. For example, if we have Z over Z minus half. In this particular example, this sequence, which is an anti-causal sequence, later on you realize that x of z also have exactly the same Z-transform. The only difference is that the region of convergence is that the absolute value of z must be less than half, while on the right hand side, the absolute value of z must be greater than half. So go through the math and you'll realize that although they have the same Z-transform, it is the region of convergence that differentiates between the two. Hence, if we are dealing with bilateral transform or sequences that exist on the left and right hand side, then we must always state the region of convergence. But if we are interested in only unilateral Z-transform of causal sequence, then the region of convergence is always this particular case here. It is external to the furthest pole. If we have anti-causal signal, then the region of convergence is inside the pole that is nearest to the origin. And if we have a sequence that have both left and right hand side, then the possibility is that when the two regions of convergence intersect with each other, then we will have a ring. Of course, we will have the issue that when the two regions of convergence does not intersect, then the Z-transform does not exist. So go through this example to see why the two Z-transform of two very different looking signal looks the same. Finally, one interesting take-home message is that this is for the anti-causal signal with half as the pole and the region of convergence is inside. We immediately can know that this is an anti-causal signal. U minus n minus 1 multiplied by where the pole position is, and this is half to the power of n. There's a minus sign here. Later on you will see if you derive the equation. This sequence, even though it has a Z-transform, actually grows unbounded. What do I mean? Look at the picture here. At time n equals to 0, we have 0 because it starts with u minus n minus 1. And we have 1, we have a larger value 2, larger value 4, and so on and so forth. It grows unbounded. And later on, when you study stability, you will see that the region of convergence, which is the green shaded region here, did not include the unit circle. It will be shown to you that when the region of convergence touches the unit circle, then the sequence will converge. In this particular case, the region of convergence does not touch the unit circle. We can be sure that the sequence will diverge, even though it has a Z-transform. And the reason why it still has a Z-transform is because it is exponentially bounded. Although it's exponentially growing, it is growing slower than z minus n for certain z. And here, the certain z is on the green shaded region. As a last example of Z-transform of two-sided sequence, infinite sequence, we have one guy 0.9 to the power of n on the causal side. And because it's 0.9 to the power of n, as n goes to infinity, it becomes smaller and smaller. At the other side, we have 1.2 to the power of n, and you would think it's growing, but because it is this 1.2 to the power of n is only dealing with the anti-causal side, as n grows larger, 1.2 to the power of n becomes smaller. So you'll figure out that 0.2 is a pole position, 1.2 is a pole position. And you can take the Z-transform of these two separately because this is a linear system. So this is for xn, this is for yn. Both of them have different region of convergence. The causal sequence have a region of convergence external to the pole, which is external to 0.9. The anti-causal signal has a region of convergence that must be smaller than this pole, less than 1.2. Right? Where is 0.9 and 1.2? Here and here. We draw two rings around it, and fortunately, the rings intersect. And not only does it intersect, it includes the unit circle. And hence, we can be sure that the sequence, although it is infinite, will never blow up. So later on, when we study stability, plotting the pole and the zero diagram allows us to see whether the ROC intersects with the unit circle, and if it does, we can immediately conclude that the sequence will converge. So where is the pole position? We should have drawn it here. 0.9 is positive 0.9 plus J0. 1.2 is positive 1.2 plus J0. So we should have drawn these two pole positions here. So pole at 1.2, pole at 0.9. So a picture like this is sometimes called an annulus. So this is the term, the technical term for it. The region of convergence is an annulus, and in this particular case, the intersection of this ROC is not empty, it forms this annulus, and therefore the Z-transform of this sequence exists. You can study some more Z-transform in these slides over here for additional reading. Thank you.